induction employed in piston engine to add large amount of power to their motor. Right? You can see here supercharger or turbocharger. It is basically to boost up the amount of power generated by the piston engine. So in the aviation fields, supercharging and turbocharging allows piston engine to develop maximum power when operating at high altitudes or boost its power during takeoff. So normally, the kind of supercharging and turbocharging can provide a booster, a maximum power, especially when cruising at high altitude. The pilot decided to increase the power, so they can use the advantage of having supercharging or turbocharging piston engine. At high altitudes, an unsupercharged engine will lose power. Because of what? Because of the reduced density of air entering the induction system of the engine. And that's what happened for unsupercharged engine. Okay, when the aircraft travel at very high altitude. So both superchargers, which will be shown in figure 4.8 and figure 4.9 for turbochargers, have compressor mounted in the intake system and used to raise the pressure and the density of the incoming air. Especially, it is very useful at very high altitude or during the takeoff. The advantage of compressing the air is that it lets the engine stuff more air into a cylinder, right? What does it mean? More air means that more fuel can be stuffed into, right? So you can have more air, you can have more fuel to be injected in the system. So more power can be obtained from each explosion in each cylinder. All right. So this is a figure of a supercharger. So imagine there is an engine, right? Piston engine. There is a compressor installed, right? Compressor installed so that the air can be compressed before it is being supplied into the engine, right? So this is a supercharger. You can find a picture easily in the Google to see how it looks like in a real life, right? For the turbocharger, a typical layout of an engine is shown here. This is engine without turbocharger, and this is the engine with the turbocharger. You can see here for engine without turbocharger, you have the ambient air inlet. We have the compressor wheel, air being bled into the compressor, airflow into the piston, right? And air being out the red colored diagram here, right? Shows the exhaust, hot gases. The blue one is the cold air going into the system, into the engine, and the hot air is being denoted by the red colored font, of red colored line. And you can see here there is another turbine wheel that allows the air to be discharged. When you see the other figure that have the turbocharger, right? So you have the intake manifold, right? You have the in the blue configuration. So there's the air coming into this way, from bottom, being sucked into the engine, right? And then there is a turbocharger. The turbocharger will allows air to be sucked. More air can be sucked into the engine. There is a throttle body over here before the air being pumped into the respective cylinders, the pistons, and then the hot air gases is flown through the pipe underneath here, the red zone, and being discharged at the behind over here. Okay. So the typical boost provided by either a turbocharger or supercharger is around 20 to 50 kilopascal. These two types of compressor are used in supercharger and the turbocharger. So these are either positive displacement or dynamic. And three types of positive displacement compressors are extensively used, namely the roots, the vane, and screw type compressor. Roots compressor, vane compressor, as well as the screw type compressor. The two type of dynamic compressor use either centrifugal type of compressor or axial type of compressor. Alright. So this power to supply, which can be supplied by a separate drive for the supercharger by connecting the supercharger directly to the engine shaft, or two gas turbine driven by the engine exhaust gases. As shown in figure 4.9, the turbocharger consists of a centrifugal compressor coupled to a radial inflow turbine through either vaneless or vane diffuser housing. Probably it's best for me to go back and to show you the shape of the turbocharger over there. It is a centrifugal type and it is being placed to couple the intake air intake manifold before it goes into each one of the piston. So the key difference between a turbocharger and a supercharger is its power supply. Alright, so superchargers are mechanically driven directly off the engine through belts, okay, gears, shaft or chain connected to the engine crankshaft. It is normally located between carburetor and inlet manifold. So if we go back here, schematic diagram, basically the engine itself has a mounting. It is connected by a belt or a chain mounting that is connected to a gear that turn the compressor. This is where the air coming in into the compressor before it being compressed to go into the engine. All right, that's what we mean by the explanation over here, right? Whereas a turbocharger is powered by a turbine mounted in the exhaust stream, which is spin the compressor element situated between the air intake and the carburetor or injector, as shown in figure 4.9. So what happens is that there are trade-off in both systems, whether you have a supercharger or a turbocharger. In theory, a turbocharger is more efficient because it is using the wasted energy of the exhaust stream for its power source. Basically, the turbine connected to the piston is then driving the centrifugal compressor in the turbocharger. Okay. On the other hand, a turbocharger causes some amount of back pressure. So this is the disadvantage in the exhaust system and tend to provide less boost until the engine is running at higher RPM. So it is only beneficial at a high speed, a higher RPM. Okay, compared to a very low RPM, it does not make any difference. Generally, turbocharging is commonly found on high power 4-stroke engine application, but sometimes it also can be used on the 2-stroke engines. The superchargers are easier to install, okay, but tend to be more expensive because you have all the mechanical parts. A supercharger is a lot safer because of the simplicity of its design. So you can simply connect it. The supercharger or the turbocharger are used in the following aircraft, for example, like Spitfire Mark 1, Hurricane Mark 1, Defiant fighter, Wellington bomber, Halifax bomber, Lancaster bomber, as well as the Mosquito fighter, as shown in list in table 4.3. So this is a table showing the supercharger versus turbocharger, right? Parameter, for example, like driving method. What happened in the supercharger? Supercharger being driven by compressors, by the power taken directly from the engine via belts, gears or chain, right, as shown in figure 4.8. Whereas a turbocharger, the compressor is driven by a turbine that is driven by the exhaust gases, okay, as shown in figure 4.9. Advantage of a supercharger, it drives vehicle to faster speed. However, turbocharger, the main advantages is basically high fuel economy. Okay, so disadvantages of a supercharger, they have losses due to mechanical friction because it is mechanically driven, as well as more expensive. But for a turbocharger, it can increase engine back pressure and it also less expensive. Okay. Okay, right. We have already looked into 4.1, intermittent piston engine, milestone, and types of aero piston engine, right? We want to move to another big topic over here, okay, 4.2, which involve aerodynamics and thermodynamics of reciprocating ICE engine, okay? So, a lot of the materials that we are going to discuss also related to chapter 3, the gas power cycle. Some of the terms, some of the terminology, some of the item discussed are already being touched earlier in gas power cycle. So you may want to also relate, but I would like to give a kind reminder of the symbols. Some of the symbols being used in this textbook, as already highlighted, um, when we discuss chapter 3, right, we use the textbook of thermodynamics from Chengel, Yunus Chengel et al. So, but now we back into the main reference. Okay, so some of the symbols I will highlight which one, especially the specific heat capacity. So we will, instead of K in chapter 3, now we go back to gamma. Okay, so I will remind you from time to time so that you won't get confused. Okay, let us look into the first one, 4.31, terminology for four-stroke engine. This particular figure, figure 410, shows a nomenclature for reciprocating piston cylinder engine. If you still remember, chapter 3, we also have a small section talking on the reciprocating piston cylinder engine. So this is showing a sketch of a reciprocating internal combustion engine, which consists of piston that move within a cylinder fitted with two halves, right? So the arrangement itself, it has the piston itself, it has the ball, it has the cylinder wall, and it moves up and down for the piston. Okay, whereas the crankshaft here is moving in rotary motion. Okay, so over here we have some similar terminology being used. TDC and VDC, we have the stroke and the bore, we have intake valve and exhaust valve. All right. So we will be referring to this figure in the few slides that we are going to discuss. So the sketch shown in the figure 410 just now is labeled with some special terms. Okay. The bore of the cylinder is its diameter. The stroke is the distance with that the piston move in one direction. One direction, one stroke means when it goes from BDC to TDC, right? One direction means one stroke. If two stroke, it's going up and going down. The piston is said to be at the top dead center, TDC, when it has moved to a position where the cylinder volume is minimum. Okay, basically the piston here will move up until the dotted line. Okay, the volume become minimum. That is the top dead center. Okay, when the piston move down until the dotted line down here is the maximum volume it can goes and it will stop at the bottom dead center. All right. So the distance between the TDC, the top dead center, and the bottom dead center, BDC, is the largest distance that the piston can travel in one direction. So this is called stroke, right? One stroke, two stroke, three stroke, four stroke, up and down, up and down. So the volume swept out by the piston as it moves from the top dead center to the bottom dead center is called the displacement volume. And the reciprocating motion of the piston is converted to rotary motion by a crank mechanism. As shown here, when the piston goes up and down, basically this reciprocating motion will be turned into a rotary motion. The compression ratio, RC, okay, it is defined as the volume at the bottom dead center, BDC, which is maximum volume when it is at the lowest position, divided by the volume at the top dead center when the piston goes up, when it has the minimum volumes or clearance, right? The compression ratio is basically the volume of the VDC divided the volume by of TDC, right? As simple as that. And notice that the compression ratio is a volume ratio and should not be confused with the pressure ratio. All right. So we will look at the pressure ratio later on. Right. So in a four-stroke internal combustion engine, the piston executes four distinct strokes within the cylinder for every two revolutions of the crankshaft. The crankshaft revolves two times, but the piston executes four strokes. Okay, going up, one, going down, two, going up, number three, going down, four. For within the cylinder, right? Which gives a pressure volume diagram such as might be displayed electronically. Figure it for 11. Right? So you can see here intake stroke, it goes, the piston goes up, means that one stroke, then piston goes down. Compression stroke, it has a larger volume, and the power stroke expansion, the piston goes up, meaning that stroke number 3, and stroke number 4, the piston goes down. The exhaust gas go out. Okay, so this is the PV diagram, right? You have the bottom is basically the atmospheric pressure, right? Okay, this is the maximum pressure it will have in the system, right? And TDC, the top dead center, where we have the minimum volume, and the maximum volume is at the BDC. Okay, so you can try to appreciate what's happening right over here, from one station to another station until it goes back to the earlier condition. So terminology for four-stroke engine, and the first one is that with the intake valve open, what happens is that the piston makes an intake stroke to draw a fresh charge into the cylinder. And for spark ignition engine, the charge is a combustible mixture of fuel and air. Right? Air alone is the charge in compression ignition engine. So with both valves closed, the piston undergoes a compression stroke where the station number 2, okay, raising the temperature and pressure to the charge, and this requires work input from the piston to the cylinder content. Combustion is induced near the end of the compression stroke in spark ignition engine by the spark plug. And in compression ignition engine, combustion is initiated by injecting fuel into the hot compressed air, beginning near the end of the compression stroke and continuing through the first part of the expansion. Combustion process result in high pressure, high temperature gas mixture. And the third stroke, a power stroke, follows the compression stroke, during which the gas mixture expand and the work is done on the piston at its return to the BDC. Finally, the piston then executes an exhaust stroke in which the burn gases are purged from the cylinder through the open exhaust valve. So that's very important to understand the terminology of a four-stroke engine. Okay, I hope you can really appreciate what happening. Stroke number 1, number 2, number 3, number 4, how it looks like in the PV diagram, because later on we will use that understanding for our examples. Let us move into the next one, air standard analysis. Okay, you can then relate back into your understanding of chapter 3, the gas power cycle, where we have assumptions. So there are few assumptions that we will recap back so that you can apply it for this piston engine. The analysis of real flow within internal combustion engine is very complex, right? Remember the same concept. We want to simplify. Because why is it complex? Because it is due to mechanical and thermal losses associated with the friction and combustion process. The other complexities are associated with heat transfer between the gases and the cylinder walls, as well as the work required to charge the cylinder and exhaust, the product of combustion. So accurate modeling of reciprocating internal combustion engine normally involve computer simulation. Alright? So to conduct elementary thermodynamic analysis of internal combustion engine, we can do simplification. One procedure to employ air standard analysis having the following elements. The first one is that the almost constant pressure intake and exhaust strokes are assumed to be constant pressure. Say we assume it happened at a constant pressure at WOT, or what we call it as the wide open throttle or fully open throttle valve. The intake stroke is assumed to be at a pressure of 1 atmosphere. Okay, at partially closed throttle or when supercharged, inlet pressure will assume a constant value other than 1 atmosphere. The exhaust stroke pressure is assumed at the same constant 1 atmosphere. That's the first one. Second one is that all processes are internally reversible. Okay. The third assumption is that compression and expansion strokes are approximated by isentropic processes. What do we mean by isentropic? It means that it is reversible as well as adiabatic. Okay. Lubrication minimizes the friction between piston and cylinder walls, right? And heat transfer for any stroke is negligibly small to its due to the very short time when it's happened. Number 4, the combustion process is replaced by heat addition processes from an external source at constant volume, right? Constant volume process for spark ignition cycle, a constant pressure process at compression ignition cycle, or combination. We have a dual cycle where we have spark ignition and the compression ignition. The final one is that exhaust blowdown is approximated by constant volume process. Let us look at some formulas. Some of the formulas that are being shown here already being introduced in chapter 3, right? In air standard cycle, air is considered as ideal gas, right? What happens when we ideal gas? We are going to use some standard equation for ideal gas, such that the following ideal gas relation, we have equation for 2A, where PV equal to RT, pressure volume equal to the gas constant R times the temperature, and it can also be rewritten as the component of the density, right? The volume, we can just convert it into converted into the density, right? And then it can also be rewritten as the mass. Okay, PV equal to MRT. Similarly, with the specific heat capacity at constant pressure and specific heat capacity at constant volume, right? For you have the changes dH, the enthalpy, okay, and then the internal energy U, right? And we also have the speed of sound A equal to square root of specific heat ratio gamma. Okay, this is the different symbol that being used in chapter 3. We use symbol K, but now we go back to symbol gamma, gamma RT. All right. For isentropic process, you will be using this again and again for many examples that I'm going to show you next Monday. Okay, PV to the power of gamma equal to constant, and TV to the power gamma minus 1 equal to constant, and TP to the power of 1 minus gamma over gamma is equal to constant for isentropic process. And for the work done for isentropic process for state 1 to state 2, right? So we have the work done for stage 1 to stage 2. Basically, you have the PV differences at station 2 to station 1, state 1 over 1 minus gamma. So you can convert that, can be expressed as equation 4.5. Okay, so that's the standard cycle, standard air standard analysis. So we will be using equation 42A, 42B, 43, 44, and 45 in the thermodynamic analysis of Otto cycle and the rest for diesel cycle at the same time, right? So we will now move into 4.331. Okay, so we will definitely not going to be able to finish all. We will try to finish, we will try to cover part of the item of thermodynamic analysis of Otto cycle today, and then we will continue next week. We try to see how far we can go for today's session. Right. For the engine cycle, two cycle will be discussed here. If you still remember, in our chapter 3, we have the Carnot cycle, we have Otto cycle, we have diesel cycle, Stirling cycle, Ericsson cycle, Brayton cycle, and Brayton cycle with regeneration, cooling, and so on, right? But for today, we are going to look into, for this topic, we are going to just cover on the Otto and diesel cycle, which is relevant to the piston engine. Otto cycle is the ideal cycle for spark ignition engine, whereas diesel cycle is the ideal cycle for compression ignition cycle. One is SI, the other one is CI cycle, CI engine. Specific heat of air are functions of temperature, where temperature within piston engine may vary from room temperature to several thousand of temperature. Okay, at low temperature of the cycle during intake and start of compression, the specific heat value being used normally gamma equal to 1.4. Meanwhile, at the end of the combustion, due to temperature rise, the specific heat ratio becoming 1.3. Right? So there are cases we are going to use gamma equal to 1.4, but after temperature rise, gamma will be 1.3. All right? But what happened is that to simplify the cycle analysis, right? Some of the situation we will inform that specific heat will be assumed constant, having a average value of 1.35, and this is not 1:35. I'm very sorry, it is 1.35. Basically, we take average of 1.4 and 1.3. This is also wrong. I will send you the corrected version. This is 1.4, this is 1.3, and the average value of specific heat ratio is 1.35. Okay, so in the following section, we will be using the specific capacity of 1.108 kilojoule per kilogram Kelvin. Right, I will also correct this. Is slightly wrong there. And the specific heat capacity at constant volume to be 0.821 kilojoule. And the gas constant equal to Cp minus Cv, you get 0.287 kilojoule per kilogram Kelvin. And the Cp over Cv is 1.35. So equation 4, 6a, 6b, and 6c will be used in many examples. In most spark ignition engine, okay, the piston executes 4 complete strokes, which means 2 mechanical cycles within the cylinders. And the crankshaft completes 2 revolutions. It turns 2 times for each thermodynamic cycle. So these engines are called 4-stroke internal combustion engines. A schematic diagram for the ideal cycle drawn for PV and TS diagram is shown in this figure, 412. You have seen this in chapter 3 earlier, right? So the PV diagram, so we have the isentropic compression, right? From 1 to 2, 2 to 3, where the heat being added, 3 to 4, isentropic expansion, and 4 to 1, where we discharge or the heat being expelled out of the system. All right. Let us look into the detailed thermodynamic analysis for the Otto cycle that being shown in the previous PV and TS diagram. For process 0 to 1, what will happen is that constant pressure suction where intake is happening, stroke of air at ambient pressure P naught. With the intake valve open and the exhaust valve closed, the piston makes an intake stroke to draw fresh charge, a combustible mixture of fuel and air into the cylinder. It's being pumped into the cylinder. All right. So in this case, P1 equal to P5 equal to P naught. So you can see here P1 equal to P5 and also equal to P naught. All right. So in the beginning, at the beginning, right? At the same time, the work done from 0 to 1 equal to the P naught, the pressure at 0 at the beginning times the volume difference, V1 minus V naught. Here, specific and total volume. Specific volume is small v, total volume is capital V. So just put in mind that what we mean by the symbol. Small v, specific volume, capital V is the total volume. For process 1 to 2, isentropic compression happen with both valve closed. The intake and the exhaust both closed. The piston undergoes a compression stroke. Okay, what happens is that it will raise the temperature and pressure of the charge. This requires work input from the piston to the cylinder content. So we have isentropic equation that we have already introduced earlier, right? For station 2 to 1, so you put the specific volume and the total volume. You can also use the total volume and where we have the compression ratio, okay? And equation 4.8b, this is for the pressure, right? So you can also use the same approach. And we know that the heat addition at station 1 to 2 equal to 0. It is adiabatic for compression. And the work done from 1 to 2, you can express it in PV over 1 over 1 minus gamma, right? And you can rewrite that for in terms of the internal energy as well as the constant specific heat at constant volume, CV, and the difference between temperature 2 and 1, right? Process 2 to 3, constant volume heat addition. This is where combustion happening, where heat being added. Okay, T3 is at Tmax, maximum temperature. P3 also Pmax at the maximum pressure. V3 specific volume at 3 equal to specific volume at 2, which is at the top dead center. And we know that over here there's no work done. Work equal to 0 for 2 to 3. Specific heat added, the Q in the system, basically you have Q to 3 equal to Q in equal to the specific constant at specific capacity at constant volume time the temperature difference between 3 to 2, and you also can be expressed as the internal energy from 3 to 2. All right, so you can work it out. Q in equal to the mass flow for the fuel times the heating value for the fuel, normally being given in any equation, and the efficiency for the combustion chamber. All right, so you can also express it in terms of the mass of the air plus the mass of the fuel times the specific heat capacity at constant volume and the temperature difference, right? So you can get this expression down here. All right. Over here, the symbol QHV is the heating value of the fuel. So depending on type of fuel that you are using, normally in a problem solving, we will be given you QHV value, right? Meanwhile, the AF is the air to fuel ratio, right? Also normally being given the air to fuel ratio or mass over of air divided by mass of the fuel, air to fuel ratio. Combustion process results in a gas mixture having the maximum pressure and maximum temperature. Combustion is induced near the end of the compression stroke by the spark plug. Right. The final part is the process of 3 to 4. Isentropic power, or we call it as the expansion stroke. Right? What happens is that the compression stroke during which the gas mixture expands and the work done on the piston as it returns to the BDC, bottom dead center. All valves are closed. The intake and the exhaust are closed. So you using the same approach for isentropic expansion, okay, and for temperature and for the pressure, right? You know that Q34, there's no heat addition or heat release. It is still at the expansion stage. And W34, the work done, can be expressed as the internal energy as well as the specific capacity at constant volume and the temperature difference between T3 and T4, right? Finally, process 4 to 5, constant volume heat rejection, where the exhaust valve is open, intake valve is closed. Okay, so you know that the specific volume at 5 equal to specific volume at 4. It happened at the same volume, and specific, which is equal to specific volume of bottom dead center. The work done 4 to 5 is 0. So you have the Q out, you put the expression of Q out, and you can get it by this expression. All right. And the last part, process 5 to 0, you can go back from 5 to the earlier state where constant pressure exhaust stroke at P naught, which is equal to the beginning of the pressure. The piston then execute an exhaust stroke in which the burn gases are purged from the cylinder through the open exhaust valve. Right? So you have expression P5 equal to P1 equal to P naught, and W, the work done from 5 to 0 equal to the P naught times the specific volume difference between 1 and 0. Okay, Now we want to look at before we end, we have a few more slides. We want to look at the thermal efficiency of Otto cycle. Right? So since Otto cycle is executed in a closed system and disregarding the changes in kinetic and potential energy, KE and PE is being neglected, the energy balance for any process is expressed on a unit mass basis, and the work done equal to Q in minus Q out in terms of kilojoule per kilogram, and the work net, the total net work is basically can be also expressed in terms of the internal energy different at 3 to 2 as well as a minus 4 to 1 internal energy. The thermal efficiency of the Otto cycle can be expressed as W net over Q in. So you can put in term of the expression that either in term of the internal energy or in term of the specific heat capacity at constant volume for the respective temperature difference, right? And you rearrange that to get the equation for 14A, all right? So what happened is that since processes of 1 and 2 as well as 3 to 4 are isentropic, the volume are the same for station 2 and 3 and station 4 and 1. So replacing the values, you can get the temperature ratio 2 to 1 equal to temperature ratio 4 to 3. You can rearrange that to become this expression. So from equation 414A, 414B, 414C, what happens is that the thermal efficiency of the Otto cycle can be rewritten as this expression 415, all right? So which is earlier being defined, right? Where we know the RC, the compression ratio, equal to specific volume 1 over specific volume 2. From equation 414b, the thermal efficiency is dependent of both the compression ratio, RC, and the specific ratio, gamma, right? A plot of Otto thermal efficiency versus the compression ratio at different specific heat ratio, gamma, is given in figure 413. You can see here for different type of gases, gamma equal to 1.3 is this solid line, right? And gamma equal to 1.4 is this dotted line in the middle, and gamma equal to 1.667 is the smaller dotted line above here. Alright, and this is the plot of Otto thermal efficiency, gamma zeta TH, and the compression ratio RC. Okay, from let's say RC equal to 1, everything is efficiency is 0, right? And if compression ratio equal to 10, you can see already the thermal efficiency of the Otto cycle for different type of specific heat ratio, different type of gases will be different. Alright? From this figure, okay, it is noticed that the thermal efficiency is rather steep at low compression ratio, as what I already explained just now, but flattened out starting with compression ratio value of about 8. And you can see at about 8, it more or less it already flattened compared to the angle, this the slope here, and the slope getting less and less until it is flattened above compression ratio of 8, right? So increasing the thermal efficiency with compression ratio is not as pronounced at high compression ratio. It is applicable at a low compression ratio. For a given compression ratio, ideal Otto cycle using monatomic gas, such as argon or helium, which has one atom, monoatomic gas, as a working fluid, will have the highest thermal efficiency. The least specific heat ratio provides the smallest autothermal efficiency. So we will end our session today with the general remarks. The first one is that the working fluid in actual engine contains larger molecules such as carbon dioxide, and the specific heat ratio decreases with the temperature, which is one of the reasons that actual cycle have lower thermal efficiencies than the ideal Otto cycle. So second general remark is that for a given compression ratio, the thermal efficiency of an actual spark ignition engine is less than of an ideal Otto cycle, and because of the irreversibilities, normally friction and other factors such as incomplete combustion that will also resulted in the thermal efficiency of an Otto cycle. Finally, the thermal efficiency of actual spark ignition engine ranges around 25 to 30% only. All right. So with that, we will continue on Monday. All right. On the following, we are still going to cover a bit more on thermodynamic analysis of Otto cycle. We haven't finished yet. We will continue from here, and we will look at the other example. There are few examples, equations, and example calculation will be introduced later on Monday. Okay. So with that, thank you for your attention.